Okay, we'll get started then. It's it's 8th week. It's kind of crazy. All right. I'm just taking a look at data camp. Most of you guys are keeping up with the homework, so that's great. We're consistently at around 3 or 4 for missed, and I think these 3 or 4 people just completely dropped the class. So it's the same people here. Maybe a couple people are behind on the Pandas Foundations. That one was a longer one, but you guys are all keeping up. I know I have SQL due this week, and then we start doing Scikit-Learn and whatnot. But I'm going to do Scikit-Learn this week and next week, and then we'll do SQL later. So that's just rearranging some of the stuff. So my apologies if the lecture content does not align with maybe what you're doing in data camp, but I don't know if it ever really did. So just kind of sort of thematically related, but maybe not exactly the same. So, okay. So let's talk Scikit-Learn. So, well, I don't know. Do I need to say anything about the midterm exam? We still have to grade them. I just took a quick peek at a few people's submissions, and they seemed okay. So, yeah, I think last quarter I made the exam too long, so I cut it down a lot this quarter, and I don't know if it felt like the appropriate length or too short, or if it was just like, okay, we just got it in around 2 hours of time. I don't know, but what's that? It was okay?
Yeah, maybe a little more time or something like that.
A little more time would have been better? Okay, so all right, so this was around the appropriate length of time. That, like, if I put in one more question, it would have been too much.
Yeah.
Okay. All right. Okay. Well, that's good. I'm trying to figure out a good balance. So okay. And then was it helpful for me to have the graphs in the instructions so you
weren't messing up.
Yeah, so you knew like you were on the right track. Okay. All right.
Somehow when the code made it exactly like yours. It was good.
It feels good.
It feels good.
It feels good when you see that. Okay. All right. Well, good. Okay. Then I'll keep that in mind for the future. Okay. All right. Oh, I already opened this up. What happens here? All right. Let's we'll start a kernel, and all right. So this is so we'll introduce Scikit-Learn, and Scikit-Learn is probably like the most popular machine learning package for Python. And machine learning is a fancy name for fitting a model. Okay, that's all it is. All right. So, and I don't know. Did anyone like take the time to say like this is what it means to fit a model in your academic careers? Very recently.
Professor Always.
Okay. Well, that's good. All right. This is a rare occasion, but we'll pull up a notebook here. All right. So fitting a model. Let's just talk very, very briefly here. Oh dear. I can't. Hang on. Okay. My pen is all messed up here. Okay, but I'll do my best. All right. So fitting a model, the idea is you've got data, right? So you observe data. Okay, but you have to ask, where did the data come from? Right? And so is some entity out there. There's like a data generating process. Okay? Whatever this thing is, somehow this produces the data you have. Okay? And we want to know, we want to create a simplified version of the data generating process. A simple version of this thing that helps us understand the data we have. Okay, we want to just kind of so a model, that's all a model is, right? So a model is a simple version. Simplified version of the data generating process. Now, the data generating process, often in your intro classes, is treated as you've got this population and the data is generated via a random sampling mechanism. Okay, so intro classes, data generating processes. You have a population and the data is generated via random sampling. So statistical inference comes back to just estimating parameters of the population, okay?
When you say data is generated, do you mean by us? I mean, us collecting the data, or?
Well, whatever it is that, like, you ended up with data, right?
Right, that's it.
Yeah, you ended up with data. So either somebody collected it, or like
there's some sensor which picks up.
Yeah, there's a sensor that picks up the information. Something is producing this data. Okay. All right. If you have something like in like linear regression, what you have here is you have a population, and in the population there is a relationship between X and Y. All right, so I don't know, X could be, I don't know, height, and Y could be arm length, right? And there's some, there's a real biological thing happening that, creates someone's height and someone's arm length, okay? But, we don't actually care. At least in this class, we don't care, what's the biological process. We just want to know, okay, is there a relationship between X and Y? Yeah, there's some kind of relationship, and that's what we're going for. And then, we look at our data. Random sampling produces our data. And we get our data. All right, and we fit a model, okay? And our model is just a simplified version of the true relationship between X and Y. And we just say, okay, Y is going to be related to our X in a linear relationship, okay? So this is just a linear model, and all we say is that the relationship between height and arm length is linear. But the true relationship in the population could be more nuanced, okay? And there could be, I don't know, some kind of strange relationship that's not exactly linear, but we'll say, for our intents and purposes, a linear model is good enough, okay? It gets us kind of in the ballpark. It's easy to understand. We're happy with this, okay? I don't need to worry about exactly how bones grow, and I don't know whatever else determines height and arm length. And you know, we can always make more complicated models by using height to predict arm length. You can use, you know, other variables. But at the end of the day, it's just we have some kind of simple model, right? So, you know, a slightly more complicated model. I don't know, what would determine arm length? We can say arm length is equal to B0 plus B1 times height plus B2 times, I don't know, gender. I don't know if that even is related to arm length, but blah, 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 etc. More variables, okay? Plus dot, 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 you know, more variables plus error, okay? Because your model is not intended to be the end-all be-all of the relationship between these numbers, but just something to kind of get us in the ballpark. And generally, you know, we prefer simpler models that are easier to understand. So we might even prefer the just linear model with one variable. Okay. Anyway, the idea of fitting a model is just get parameter estimates based on our data. All right, and there's a few ways to do this. A lot of times we'll use maximum likelihood estimation or something, get parameter estimates based on our data, and there's, you know, different methods. And generally, they're usually some kind of optimization. Okay? So either minimize a cost function or maximize a likelihood or score. Okay, so minimize a cost function, OLS, ordinary least squares, classifies this because the goal is pick the parameters that minimize the least squares residuals. Okay, or maximize a score or likelihood. It turns out that the maximum likelihood estimates for linear model coefficients end up being equal to the OLS, but these are kind of our two guiding principles as far as how to pick parameters. Okay, in general, we're either trying to minimize something that says this is bad. Usually, it's a function of the error. Okay, but other times we can say, you know, this cost that we're going to do will not just be error, but it'll be error plus how complex our model is. Okay, and so so we want to minimize this thing, and we say, okay. Yeah, I can keep getting more complicated models, and if I make my models more complicated, the total error goes down, okay? And we can say, you know, let's include more things. But we might say, you know what, let's not just look solely at least squares residuals. Let's say we're going to add a term that says the more complicated your model is, that's going that's going to increase the cost function. Okay, and so now you have these kind of competing priorities: lower residuals, but a less complex model, and you have to weight them accordingly, and you're still trying to minimize that cost. Okay, or you might have another way to score the thing, and you're trying to maximize the score, right? And so these are kind of our strategies. And so when we talk about machine learning, it's just this process of fitting a model. It's just getting parameter estimates. You have to decide what kind of model it is. Okay, is the relationship that we're guessing is a linear relationship between y and x? Okay, or is the relationship between y and x something more complicated? Okay, that has to be described using I don't know, a more complex function, maybe like a quadratic or whatever it might be. Okay, you've got something between that relates your predictor variable x, this thing, and the output variable y, and that's your model. And then you want to say, okay, if this is my model, what are these parameter estimates? What are my estimates for B0 and B1 and whatever else we have? And you generally do that by minimizing or maximizing some kind of function. Okay, and I don't know if you guys have taken 102B, but that's kind of the subject of 102B. All right, so let me just talk about Scikit-Learn. Scikit-Learn has a whole bunch of models that you can fit, okay? And today we'll just look at linear regression, okay, the linear model, because I think that's something that's familiar enough to us that I can kind of throw it around without it being this huge mysterious thing. But I don't know how many types of models we have. Okay, if we go to like regression models, there's generalized linear models, and then linear discriminant analysis, support vector machines. There's all sorts of things. Okay, and these are all just different ways to predict some kind of numeric output. Okay, and you can have there's classification models which you use to predict a categorical output. Okay, and clustering, which is for you're not predicting anything, you're just looking for structure. Probably as far as supervised learning goes, where you're trying to predict some kind of values, you're going to be using classification or regression for numeric predictions, and all of these models are available to us. Okay, and we're just going to start off with the simplest, okay, ordinary least squares. But they all work. All of these models, okay, work in the same way, in that you declare to Python, you load up Scikit-Learn, and you tell Python, this is the kind of model I want to fit, okay, and then you give it two things. You give it an X, which Scikit-Learn calls its feature matrix. All it is just the values of your predictor variables. Okay, and then you give it y, which is going to be the I don't even know the response. Okay, just the values that you're trying to predict, or whatever it might be, and so you declare it that way, and then you create your model, and then you say fit the model based on this x data and this y data that I have, and then that's it. Okay, and then once you have it fit, then you can use it to make predictions, and you say model predict. Okay, so anyway, you can do your regular things: import NumPy, pandas, matplotlib, and here I can import sklearn, but today we're just going to do a linear model, linear underscore model. So I'm going to just do from Scikitlearn import linear model. And that means I don't have to keep writing Scikitlearn dot linear model and things like that. Okay, so so from here I'm going to just generate some data. I'm going to do just 50 random normal values. I'm going to multiply that by 10 to just create some random noise. And then so the I'm sorry, not random noise, just these are random numbers that I've got, okay, centered at 0. And then no, random, I'm sorry, I got this all in my all these things. Okay, just a bunch of random numbers. This is random uniform. I've got 50 random uniform numbers, and then I multiply it by 10, so it's going to be spaced out between 0 and 10. Okay, and then from here, the true relationship, I don't know why I have it like that. True relationship between x and y is I got 1 plus 0.8x. Okay, this is the true relationship. 1 plus 0.8x, and then I'm going to add some noise. np.random random normal, random n, 50, okay? And so when I create this plot, this is what I have, all right? So from 0 to 10, these are just the random values I have. So the true relationship is 1 plus 0.8x, but we have added some random noise to it. Okay. All right, and so to fit scikit-learn, we have our x and we have our y, and I can just kind of, this is x is just a numeric vector or a numeric array, and then so is y. These are just, they're just arrays of 50 values by 50 values. Okay. To fit this, I call scikit-learn.linearModel. Okay, and here I already have it, just linear model, and then we're going to say this is the kind of model we want to do. We want to fit a linear regression model. And then you have a few options, and I don't have a column in my X matrix for B0, so I'm going to say fit intercept equal to true. Otherwise, it just tries to fit it for your X matrix right now, which only has the X values and doesn't have something for B1, right? Which would normally be a column of ones. Okay, so anyway, I just declare my model here, and right now my model's empty. It hasn't. We haven't done anything. Okay. And here's my X. My X has 50 values in it. Okay. When you throw X into scikit-learn, it's got to be a matrix. Okay, so if I try to do model.fit, so I've declared my model as this linear model. If I tried to do it right now with just a unidimensional thing, it's going to complain. Okay, it gives me an error. It says expected a 2D array and it got a 1D array instead. So you have to just convert everything into an actual matrix, right? So this is my shape right now. So all I have to do is I just reshape it, okay? And so now I have a two-dimensional array, and if I print this out, it'll show up as two-dimensional, okay? So I've got 50.1, and so all I did was I just took little x and I reshaped it into the capital X matrix, okay? And so I just call model.fit, and I give it capital X matrix, okay? So this is a two-dimensional array. Y itself, though, is one-dimensional, okay? And so you're just fitting the input values, your predictor variables, and what you are predicting, which is just a 50 comma one-dimensional array. Okay, and that's it. and I fit it, and it says, okay, here's my model, and it doesn't look like anything has changed, but my model now actually has coefficients associated with it. Here, if I go back, if I clear everything out, before I fit the model, I should just show you what happens. So we bring this in, okay. So here's y. Before if I do model dot coefficients, it doesn't have any right now, okay? Once I convert it to a matrix and I fit it, now we've got some coefficients, okay? So after I declare the model, before I fit it, it doesn't have a coefficient, okay, for the x. But now that I have, we get an intercept. We have a coefficient, okay? So this is the value it predicts for the slope, okay, which is pretty close to what we have. Our real value is 0.8, okay, and then the real value for the intercept is 1, and it predicts 1.001, which is fine, okay? So it's not that exciting because it's linear regression, and you guys are very familiar with this, but this is the general form of what we do, okay? You have an X matrix that you're using for your predictions, and then you fit it to your Y's, okay? Once you have your model, you can use it to make some predictions here, okay? So here I've got, I'm going to just say I'm going to predict some values, and we're going to just space out from 0 to 10 here, okay? And again, I reshape this so that it's a matrix, okay? Because the models require your predictor variables to be matrices. Because generally you have more than one predictor variable, okay? So that it makes sense. And then so all you do is now that we have this model defined with coefficients and intercepts, we call the predict method, and we give it the matrix of values that we want it to make predictions for. Okay, and it does that, and these are the predicted values. Okay, and let's just do marker equals. Oh. All right. Maybe. Okay, this is maybe too many. Let me just linear space. If I just do, let's do 20 here. Okay. No. Okay, so here you can see it has created predicted values for all. Let me just do this for 21. Yes. Okay. So so this is what we have, and all it's doing is it's just plotting where it predicted, and it kind of connects the dots here. Okay, I could have done plt.scatter prediction x and y as well. Maybe this is better, okay, without the plot. So here we're just predicting for these 20 values, and we see they're in a straight line. If I just did plot and I get rid of marker, then it'll look like just a straight line. But this might be a tiny bit deceptive in that it appears that we've created this continuous thing, but all we've actually done is we've predicted values at like 21 locations or 20 locations, and we're just connecting the dots. Okay. All right, so that's basically Scikit-learn. You declare the model. Okay, back here we say I want to create a linear regression model, and then you fit the model, and fit the model requires that your predictor matrix is not capital X. Your predictor variables are in a matrix, okay, two-dimensional, and then it fits whatever coefficients it has. These don't actually even matter, okay? Scikit-learn is not intended to be used for like to decide if particular variables are significant or not significant, okay? So like in R, you create an ANOVA table, and you can say like, oh, this one has a p-value of 0.001, so we're going to keep it. This one has a p-value of 0.6, we're going to throw it away. Scikit-learn's not really intended for that, okay? You just say, here's my model, let's fit it, and it's going to give you everything. And so asking for the model coefficients and the intercepts, I would say this is probably not in the normal flow of things with Scikit-learn. With Scikit-learn, we often just fit and we predict, okay? And we evaluate how good our model is at just how well our predictions are, okay? We fit and we predict and we say how good are our predictions, and that's what we go. We don't really go off of the coefficients and the intercepts. If you want to do coefficients and intercepts in ANOVA, stats models, the package stats models is more appropriate. And I know it feels weird because we're like stats majors, and so, and you take an entire course on linear regression, and we talk about the importance of diagnostics and stuff. Scikit-learn and machine learning were a little bit less stringent on these diagnostic things. We just say, all right, let's fit it, let's see how it looks.
You can fit anything to anything.
You can kind of fit anything to anything. And so, you come back and you say like, well, how do you know if, right? I did like residual plots, right? Y minus predict, but this is, we probably never actually do this in Scikit-learn, to be honest, okay? Because this is not how we evaluate how good our models are, okay? We evaluate models by how good, how well they predict. There's generally a score function, okay, that we're trying to either minimize or maximize. In linear regression, you can evaluate your score using an R squared, okay, and we want that to be maximized. Or, and I think that's what Scikit-learn does. So every model will have a score method. So if I go to linear regression, everything has a score method, yeah. So you're gonna have a score method, and this says, it gives you back R squared, okay? If we do ridge regression, I don't know if you've learned ridge regression or lasso regression, but lasso is basically like linear regression, except there's a penalty applied to, this looks like impossible to read, but this is basically the residual squared, okay? Y minus x times the matrix squared. So this is y minus y hat squared. That's your residual plus, and you have, this is called the L1 norm of W, which is like how many things you have in there. And so you get a penalty if your model is too complicated, okay? And we try to minimize this, and we get another score, and this is also the R squared. But yes.
Do you get a penalty to avoid overfitting, or what is the reason?
Yeah, so this is not technically a machine learning course, but I have to like cover certain machine learning concepts, and so there's this idea of regularization, and it is to avoid overfitting, and it's to avoid producing a model that's too complicated and overfits the data. And so you introduce penalties for making your model, every time you make it more complicated, you introduce a penalty. And lasso is one way to introduce a penalty. Ridge regression introduces a penalty by using the L2 norm, which so this is what we have. And we just have like different ways to introduce penalties based on our parameter estimates. And so Scikitlearn just says, all right, I'm going to do my best and try to minimize this, the cost function, which is a combination of the sum of squared residuals plus the complexity penalty, all right? And so so when you have both of those, it's going to try to minimize the residuals and minimize how complex the model is, and you get some numbers, okay? And then we just say, all right, well, how well does this predict, okay? Now, if you have, I probably have to cover just some very basic cross-validation because that's like a key part of using Scikit-learn. And so in cross-validation, we take our entire data set and we chop it up. I don't know if I'm going to run out of time. I'll talk about this some more. But there's kind of a different philosophy behind using Scikit-learn and R for fitting models, okay? Or even stats models, okay? So stats models is probably more in tune with what you're accustomed to as stats majors who are familiar with R. Because in stat, you know, in your regression class and your design of experiments in ANOVA course, we had all of these things that said, this is the kind of model you're fitting, these are the diagnostics, this is based on the central limit theorem, so you want to make sure you're not violating these assumptions. And I think that's still very important. But Scikit-learn is a little bit more of a, let's let the data speak for itself, okay? And we'll just fit a model and we'll see how good the predictions are. And to kind of make sure we're not overfitting the model, let's split our current training data into like subsets of training and test sets, and we'll kind of check how well we perform on these little mini test sets before you go to like a real actual test data set. And I'll explain that concept in a bit, I guess on Wednesday or something with cross-validation. But that's what we have, okay? I'm going to just fly through this Boston housing data set example, okay? There's a few data sets already built into Scikit-learn, and they come in things called bunches, okay? Scikit-learn a bunch. And a bunch is basically a dictionary, except it's a dictionary, but the data and target and all of the different things are kind of stored here, okay? So the data, this is going to be your predictor X matrix, and then the target is the vector Y that we are trying to predict, okay? So if I look at the data, we have a two-dimensional matrix, 506 rows, 13 columns, and then the target is just the 506 values, one-dimensional vector that we're trying to predict, okay? The other things, we've got, feature names. These are the names of the columns in this matrix. And then Boston.description is just basically like the help file for the thing. And then the other thing is the file name, which is actually where the data is stored on your computer, okay? Boston.data itself is just a matrix, and as we saw, it was two-dimensional. And just to kind of, I could just use this and go straight into Scikit-learn, but to kind of make it a little bit easier for me, I'm going to convert it from a NumPy array into a data frame, okay, and give it column names, okay. So here, if I make it a data frame, I just have the columns. The column names are 0 through 12, which is not quite handy for me. So all I'm going to do is I'm going to just say, all right, I'm going to just take this vector of feature names, or this array of feature names, and just make it the column names. And so now I have, it's still the same exact data, but it's just now in a data frame, and I put it in a, I gave it column names, okay? And then we can see, you know, the target is still our one-dimensional thing that we're trying to predict, okay? And I guess just for, I forget why I chose to do this, but I decided to just attach the price column that we're trying to predict to the data frame itself.
Maybe
Okay.
you're used to R.
Huh?
Maybe you're used to R.
Yeah, maybe. I'm trying to, but okay. But anyway, the fitting of the thing is we're going to do linear regression, okay? And then as far as our X matrix goes, I'm just taking the columns from crime to LSTAT, okay? So I'm not including the target in our predictors matrix, you know, obviously, okay? And then so all we do is we just try to fit, you know, X to the target, okay? So we've declared that we want a linear regression model, and then we just do the same thing as before with X and the target, and that's what we get, okay? Again, you know, calling coefficients is probably not a common thing, but we could, and we get coefficients for each of these variables, okay? But like I said, you're not going to get an ANOVA table that says this coefficient's significant and this one's not significant, okay? That's not how Scikit-Learn thinks about these things, okay? And so all we do is we say, okay, well, this is the model I did. Let's make some predictions, and we can kind of just compare these things, all right? And this is predicted versus actual, and we're hoping to see a linear relationship. And it seems like for the most part up to here is pretty good, except it's just that when the actual prices go over 40, and there seems to be a cap at 50 for whatever reason, maybe our model doesn't perform as well. Okay, and then, you know, we can just ask for the score, which is basically the R-squared value with all of these things, and we get a score of 0.74. Okay, now this might scream against kind of your training, your statistics training, and it probably should, okay? Because this idea of just saying, here's my entire thing, and let's just throw everything at it, and I'm not going to do any kind of reconsidering, probably feels very wrong, okay? And I would say, I would agree with you, okay? But if we take away your tools of like ANOVA and figuring out p-values associated with each thing, how can we prevent overfitting, okay? And so this is kind of the strategy that Scikit-Learn is employing. And so we'll talk about that on Wednesday. I know Wednesday is the day before Thanksgiving, and so maybe not all of you will come to class. That's okay, huh? Yeah, but I'll be here, okay? I'll be here and I'll record it, and you guys can watch. But that's what we'll do. Okay, so maybe I'll see you Wednesday.